Okay, the next thing we're going to do is cams in motion displacement graphs. So we've got the assembly completed now for our two cams, and we're going to do the eccentric cam as an example, and then you're going to pick one of the other cams for your submission. Okay, so if we look at this, what we're looking at here, we need to get a whole bunch of measurements from Fusion for our follower displacement and from our cam displacement. Okay, so I've already got the cam measurements recorded here, and this is in your day-by-day lesson plans, so you can create a copy of this file and then do your pair, your snail cam, or heart cam, or whatever you did. Can't do the circle cam, you got to do something more complex than that. Okay, so let's see here. Go back to Fusion. Let's look at how we might get the cam displacement, because that's probably the easiest. If we go look at that, let's look at the cam displacement, and the easiest thing to do is just go ahead and put another sketch on there, and let's go ahead and project. If it's not there, I want to project the circle, because then that also gives me the or I don't need the circle. What was I doing? What I want to do, I want this origin there. So what I want to do, I'm just going to draw some lines. I want to draw a vertical line, and then I'm going to draw a line here that's a 135 or a 45 degree angle. Or I could just draw it. Let's see, I got out of proportion there. Draw it D to dimension 45 degrees. Let's draw another line that comes straight across, so that would be a 90-degree rotation. So that time I got it in there okay, and let's come down, and I'm going to have to dimension this one, so we'll go D for dimension. Here to here, that's another 45 degrees. And then let's do a vertical line, of course, from here to here. Okay, so now what we're going to do is reference dimensions, or what's called driven dimension. So then there's my ½ displacement. It gives me a message that says, hey, this is going to over constrain it, so this is just a driven dimension. But that's a ½ inch. That line segment is 0.582. This line segment is 0.866. And this line segment aligned is 1.289. And of course, that one is 1.5. So you can see here I have a 2-inch diameter cam. It's my nominal diameter, but I have a ½ inch minimum displacement and a 1.5 inch maximum displacement. So therefore, okay, so that's my minimum and my maximum displacement. And I have all those reference numbers, which I've then recorded on my eccentric cam. Now, of course, I could keep going, but after you go past 180 degrees, the numbers just repeat themselves. So there's no point in doing the other measurements. You're going to want to do that for the snail cam and the pear cam. The hex cam is every 30 degrees. That's pretty easy to do. And then the heart cam, you got to go about every 15 degrees to have enough numbers to generate a graph. So if you were an overachiever and tackled the heart cam, you get more work. Okay. All right. So next, what we want to do is, we'll go ahead and save that. And that might be showing then in the assembly. So if I go back to assembly, might have to update that. And next what we want to do, we want to measure is the distance of the top of the follower to the top of the box. That's your follower displacement. And of course, what we want the students to recognize is these graphs are going to be the same. So first thing we want to do, if we're not at the origin still, let's double click this vector and make sure we're at 0 degrees, that first revolute vector that's on the crank there. And it won't change because it's already 0 degrees, but if it's off, let's go down there and go 0 degrees, make sure it's 0. So then using the inspect tool, and let's go ahead and measure 3 decimals of precision is good. And we're going to measure from the top of the follower to your top of the box. Okay, and that gave me a measurement of 2.438, which is, I believe, what we have over here, 2.438. Okay, and then let's go back. And what we need to do is just generate all the needed measurements for every degree. So now here on my vector for my revolute, let's go ahead and go to 45 degrees. And at 45 degrees, we'll again inspect and measure each one. Okay, and that is 2.535. So then we'll go back and we'll want to record that 2.535. And so on and so forth. I'm having trouble getting that vector up. There it is. Oh, I got to close that box. That's why. There it is. 90 degrees. Let's measure top of the follower, top of the box. $2.839. Okay, so now I've got all my angles there. So then the next thing we want to understand is how to generate the graph. So I did all my measurements for all my angles. So now what I'm going to do is I'm going to go ahead and highlight my data, and let's insert a chart. And that would just be a line graph. And you could clean that chart up if you wanted to, but not a big deal. Click in free space. Let's see, I need to zoom out back to 100%. Okay, so we could clean up the labels if we wanted to, but the main point here is what we see is that what is happening above the box is the same thing that's happening with the displacement inside the box on the cam. Okay, and this is kind of a preview of where you're headed with the next one, but if I would highlight the eccentric cam and the cam displacement, this is a preview of what we're going to do in lesson 17, in block 17, and insert a chart. Instead of a line chart, we're going to go down to radar. And where's radar? Oh, can't do radar. One little mistake there with that. To do radar, we want to leave out the 360, I think. So insert a chart, because 0 and 360 are the same. And here's the radar chart. So we don't have enough points there, but that's now giving us the basic eccentric cam shape. If we had more points, it would look much more like the graph that the cam that we're using. Okay, so that's the cams in motion.